Welcome back to the workshop. We want to continue taking a look at section 4.2, paths and circuits. For our next example, we actually want to take a look at a definition. It's pretty simple, so this should be pretty quick for us. But it's just discussing when a graph is connected or not connected, and what exactly that means. And it's pretty much as straightforward as it would sound. So let's take a look at our notes. A multigraph, and hence graph, of course, because every graph is a multigraph. So a multigraph is called connected if there is a path between every pair of vertices. Okay, so a graph is called connected if I can move from one vertex to another along some path for any pair of vertices that I want to think of or that I could choose. Okay, so let's give a few examples of connected and not connected graphs. So first, a connected graph. So for our first connected graph, we'll make it super simple and straightforward by just looking at three vertices. I can move from one vertex to another without any concern. Yeah, easy enough. Okay, what about something that's not connected? Let's take essentially just as simple of a graph. Here, I have something that's not connected. Well, visually, I can see that there's a separation. According to the definition, what I might say is that there's no path from vertex A to vertex B, for example. So not connected. There's no path from vertex A to vertex B. All right, let's look at another one that is connected. When it comes to connected graphs, it's not anything too crazy. For the most part, it's pretty observable. You can end up with a large collection of vertices, and as long as there's a way to move from one to another, then you're all set. So here is a good example because I've just drawn a single path that connects all of the vertices together. So I know I can move from one to another. And if I wanted to, I can add some more edges in here. Cool, this is fun, right? I can do this. Just an example of a graph where I can move from one vertex to another without any concern. Usually it's a pretty easy visual check when you have this sort of representation of a graph. But sometimes it's not. So let's look at one that's not connected. This one I'm drawing pretty similarly at first here. Let's see, I'm going to, let's see, I want to connect these guys. This looks pretty good. And go with these guys. There we go. Okay, so now with this, I have something that if I just glanced at it, I would think that this would be connected, right? There's a whole bunch of lines, they're all crossing each other, it's got to be connected, right? Well, what we should notice is that there's actually two components here, two pieces to the graph. And it looks like I drew them all quickly enough together that it's all connected. So let me draw it one more time, a little bit more slowly for the computer. I want to go like this, and then let's add this one. Wait a moment, and there we go. Okay, so now hopefully it was drawn slowly enough that you could see it as well. But we have two components. We have the red component and the blue component. I can travel between these four vertices all that I like. And I can travel between these four vertices all that I like. But there's nothing that connects, for example, vertex A to vertex B. Okay, so I can't move from vertex A to vertex B, so it's not connected. Not connected. All right, so that's as simple as connected and not connected is. We won't talk too much about that, but there is a little bit of an idea there that connects back to previous things that we've seen, in particular, equivalence relations. So we start to, like any good math class, try to reflect back on the things that we've already learned within the context of the things we're learning now. So watch for that. All right, I'll see you guys back in the workshop in just a little bit.